here. I'm only leave what I wrote here. So essentially the switch originally only have a, oh, who forgot to put the cap on? Yeah, let me see, I have another one here. So last time we saw the schematic, right? The schematic was like, okay, you have a push button, and then this just connected to ground, while this side is dangling, right? And also, like, according to the schematic I show you for this evaluation board, this corresponds to RB14, right? Yeah. So this RB14 was connected to nothing. Of course, when you press the button or not press the button, it's not going to cause that much of a difference. But of course, you say, without pressing the button, this is a floating, and press the button, that brought it to ground. So you still have a state change. But then again, I said I don't allow you to do any kind of change of state notice, or CN configuration. So you will have to externally connect the resistor here to do a pull up, right? So what I meant is like, okay, you need to connect the 3.3 volt here through a 1 kilo ohm resistor to this RB14 node, yeah? And where did this 3.3 volt come from? And there are the label is called forgot the name, it's a long name, PVDD or whatever, like 32, V32, right?
Pin 1 on J12 was also.
What's that?
Pin 1 on J12.
Right, pin 1, that's the pin 1, or there is also another pin somewhere, but then anyway, pin 1 is the 3.3 volt, yeah? So this 3.3 volt need to be, a lot of people say, yeah, I don't have a switch. I mean, the switch, it does not have a pin next to it. I mean, that is not what I meant. Of course, I know there is no pin next to the switch, right? But then on J12, there is a pin for RB14. They're essentially the same thing, right? So you just need to connect a resistor, one side to go to that RB14, which is probably pin 10 or something. I forgot the number. Then the other one is the pin 1, yeah? So you just put a resistor on a breadboard, and then use 2 wires. One burn it to pin 1, the other one burn it to pin 10, and then you would press this 1 kilo ohm. I mean, you will connect the 1 kilo ohm in between those, right? Now what happened is like, okay, this RB14 is connected to the microprocessor. Therefore, at the beginning when nobody is pressing it, it's a high. When somebody presses it, it's a low, right? So what you really need to do is in the while one loop, right? In your while one loop, if you have already configured everything properly, you basically just say, okay, whatever that lat h bits, that lat h2, right? I forgot the number, but I believe it's 012, the cert LED. So will be equal exclamation mark port B bits dot RB14, and then that's the only one line of code you would need. So you just put it there. I mean, you got the part 1 done. Is that clear, everyone?
Mm-hmm. Really gave us that.
Yeah. But of course, you say, yeah, if this is high, this will be equal high. Else this equal low. It will be the same thing anyway, but one line would be like that, okay? Also, like I forgot to mention, like Evan sent me an email after last time's class, and I didn't realize, people actually, your compiler, even by default, the compiler setting is different. Like some of this, like remember, like when you compile the project, it complains about like your main function has to return an integer,
Right.
not a void. And that's because he noticed that actually your compiler setting, the default setting is somewhat different. Because some of us, I mean, most of us use this like warning, just treat warning as a warning. Don't treat that as a mistake or an error. But then some of the compilers actually set up as, okay, treat warning as error. And then once this compiler encounter that kind of error, it's not going to continue to compile the project. So the project will just get stuck there, and then nothing get burned, or even like the compiling or build is not successful. So if that's the case, make sure you check the property, the project property, and make you uncheck that the warning to a mistake. But so far, like let's raise our hand if you like can completely compile the project and now like all this compiler works for you. You still didn't make it work?
Oh, I haven't actually plugged it in. I just.
You haven't tried it yet?
Yeah, I haven't plugged it in.
How about you guys? Like,
This is what we did last time.
okay.
I was able to do the blinking plus. I wasn't
Okay.
able to get the
The
second.
pre-lab
So that's
stuff
what
that we
I
did
know.
last time.
Yeah, last time.
Yeah, last time.
Okay, so I guess that problem got solved, resolved. But anyway, thank you for the note. I didn't realize that. I just feel like okay, by default everybody's setting should be the same. So essentially, that take care of that. Like you have to return an integer, okay? Because that's just a warning. That's not an error in itself, okay? And then also before I continue, I want to make sure that starting from now on, your submission will include two files. One is like put all the code into one txt, like basically WordPad, Notepad, and then save it as txt, just txt, whatever like your lab1.txt. Everything, okay, doesn't matter how many parts you have. You just like copy and paste the stuff there in one file. And then for all your execution thing, even though I said like a video, but I realized like when you sent me submit this video, it's 40-some megabytes, and the college only gave me like 500 megabytes as the space, for whatever reason.
Put it in zip folders in the already, or?
No, don't do that. So now okay, I changed the requirement here. Is like okay, you put a few representative pictures, like for example 0 to 9. You don't have to capture all 0 to 9. You just do 0, 3, or 0, 4, whatever that is, okay? Because anyway, if I look at your code, I will have a good idea whether it works or not. So I just want you to save the results in one a Word document, screenshot, and copy and paste the screenshot into that Word, and then convert later to a PDF. So all I need will be just one TXT file and one PDF file. Understand? The reason for that is just because if you zip and then I need to unzip, and then we have 10 different pictures, like a big 40 megabytes for each student. Then every time I need to delete the whole thing again and again because it only gave me 500 megabytes. That's one thing. The second thing is later on the lab is going to contain more and more pictures. I don't want to grade one's work just okay, click 20 of those pictures. It's wasting my time. You understand? So I just wanted to make it clear, okay, scroll down the PDF. I saw everything, and then I give you the point. Make my life easier, because otherwise, I don't have all that time to just keep clicking on picture. Each picture is 4.2 megabytes or whatever. That eat up my space very quickly, and also it's not convenient for me. Okay, yeah.
For the submission for the text,
Yeah.
text files, do you
Yeah.
have to have the header files too, or just the source files?
I just want the source file. The header file, assume everybody, unless later on, I want you to show me the header file. I mean, only when we want to configure the timer and everything, you change something to your header file, I would require that, but for now, no.
Okay.
Because everybody's header file is the same. There's not much interesting thing for me to look at. You understand? Yeah. So, any question here? So make sure everybody understand the submission requirement, okay? If I only want to mention it once in the class, because later on if you submit, if it's not the same, doesn't comply with the rule, then I'm only give you 50 points, even you get 100 point right, okay? 50 point. You need to learn your lesson how to follow instructions. Understand? I mean, even though in the past I have keep mentioning this, people still just do whatever way they want. Give you zip file, 20 different image, you download. I mean, consider here, okay, the DTCC, the Wi-Fi thing, okay, take me long time, for your video. Take me 5 minutes to download the video, and then it's not that interesting for me, just see 0 to 9, right? so essentially, yeah, so not worth it. That's right, exactly right, because that's not the best use of my time, okay? And so essentially I want everybody to be clear, okay, of what's the right submission, because later on if you don't follow, if you still give me the zip file, I don't care. I submit it, and then in the end, right, 50 points max. So if you want to do that, that's fine, okay? Understand? Okay, good. So for this one, let's get back to this one. So essentially the pull-up resistor has to be connected from the external circuit board. And then the J12, right, the schematic I showed you last time, you just need to find the corresponding pin and then make the needed connections. And you were giving all the cables, like the female to male connection cable, you were just using those cables and then put a 1 kilo ohm resistor on the board and then do the connection, okay? Is that clear, everyone? Yeah, good. So the second problem was like for you to blink the 7-segment display, and we didn't give you the 7447 driver IC, right? I'm not sure if everybody has the 7447 driver IC, but let's see, if we don't have the driver, we just directly, connect our output, like 7 output of the microprocessor to our 7-segment display, right? So if you pay attention to the right up, I asked you to pass the output through a 330 ohm resistor, and then the other end will be connected to the 7-segment. So that's how you're using this resistor in series connection with the 7-segment LED. That way you can use the resistor as a current limiting resistor, right? So the working mechanism is as follows. When this voltage is output a low, right? On this side it's a 5 volt, on this side it's a low. So there's a voltage drop, a potential difference. So current can flow from this side to this side. And most of this 7-segment LED, if you look at the data sheet, requires a 2.1 volt to 2.7 volt for turn on, which means this side has to be at least 2.1 volt higher than this side. So for simplicity, let's just assume it's 2 volt. So how much of voltage will be dropped through this resistor? If I output a low here, a 0 volt here, 3 volt, right? Because I have 2 volt drop on the light emitting diode, I would have a 3 volt drop across the resistor. Therefore, according to Ohm's law, I can use 3 volt divided by 330 ohm, right? Which is about 9 milliamp. So 9 milliamp is perfect to light up this, 7-segment display. According to the data sheet, it says, the typical forward current is about 10 milliamp, right? So that's why we want to put a 330 ohm resistor here. Let's see what if I don't have this 330 ohm, right? The same is like the diode, light emitting diode or LED is a nonlinear device, which means it's not like a resistor. The current and voltage follows a straight line. And in a diode, light emitting diode, the current will shoot up exponentially after it exceed the threshold voltage. In this case, it's about 2 volt. So imagine if I don't have this resistor, if I output the 0 volt here, then you will have the 5 volt across this diode. But then there's no way the voltage can go up to 5 volts. This is only 2 volts. So this current will be just shoot up to an amp, for example. So what's the potential problem? The potential problem is like this LED might be burned because it cannot stand that current. And what's even worse is this current will flow into your microprocessor output pin, and most of our microprocessor output pin or the GPIO only have a current handling capability of 25 milliamp. You understand? So a general rule of thumb, of course, you need to refer to the specific data sheet of each microprocessor, but then a general rule of thumb is like all the general purpose I/O only have a current sourcing or sinking capability about 20 milliamp. So if you imagine if you send a 1 amp into the microprocessor, right, it's going to burn the chip, okay? If it's burned the chip, then like I said, you will see smoke coming out of the epoxy package, and then your semester end at that moment, right? Yeah, so essentially make sure, when you make all these connections like circuit, I understand this semester, the board is not a beginner-friendly thing, but then, unfortunately, that's the only thing we can find on our, online. But then I guess, this you can view it a different way. This will give you more exposure or more practice on doing circuit building. So hopefully, maybe that can help you with analog circuit or some other things, Who knows, right? Let's look at always at a positive way, right? So just do more circuit practice, which is not a bad thing. Anyway, you're an electrical engineer. You will have to be able to read the schematic and build your circuit according to the schematic, right? So very important, this 330 ohm, the R-pack. Remember the R-pack, like the 4116 R-pack I said in the announcement? This is actually just 8 resistors across the row. So pin 1 and pin 16, they're across the row, right? Like we talked about, this is a row, this is the second row. So on opposite side of the row, they're connected. So this is a 330 ohm. So for that R-pack, we have 8 resistors. So you just use them, this way. You understand? Like 1, 16, 2, 15, 3, 14, and so on and so forth. Understand? We're going to use 7 of them. Is that clear? Yeah. So like this is the right way to connect. But of course, right, there is one more thing I mentioned in my instruction. I want you to practice using that power adapter, the power jack. What I meant is that thing, like the adapter, the wall adapter with a 5 volt. This thing, right? And then we also have a jack. So you just, plug in this into the jack, and then you have 2, right? The 2 like positive and negative. The positive is the 5 volt, and negative is the ground. You understand? So what I meant is like this 5 volt has to come from the external power supply. Even though you say pin 2 on this J12 is a 5 volt, why wouldn't you use it? The reason I don't want to use it is just because I want you to be able to build circuit with the external power supply. And then later, when you drive a motor or something, requires a bigger amount of current, this thing can do it, but the pin 2 on our board cannot do it. You understand? So that's why I want you to know how to connect external power supply and add that one to the circuit. So what's important here? The important thing is like you need to make sure that ground of this 5 volt is the same as the ground of the microprocessor, because those 2 are the reference for digital high or low. If they're not shared the same ground, it's not going to work, right? This is one of the questions I ask you, like why is it important to share the same ground? Because if it's not sharing the ground, this high 5 volt or this 3.3 volt is relative to this ground. But this ground, if it's isolated ground, if it's separate from this, how would this be reference to that, So the high or low is relative to a reference. You need to have the same reference, yeah? Does that make sense, everyone? So what does that mean? It's like, okay, you need to find a ground. This ground is like this guy here. You connect a wire to ground, and then that ground also need to be going back to the ground of your microprocessor, which is probably pin 9.
There's a couple.
Pin 9? Forgot which one.
9,
anyway.
yeah.
Huh?
9, 6,
Yeah,
14.
yeah, a bunch. So you just connect one to one of them is fine, because they are interconnected. Does that make sense, everyone?
Yeah.
Okay, good. So there should be no problem on this one now, right? Yeah.
And all the grounds on the J12 are all the same ground?
Yeah.
Okay.
I mean, sometimes we just use one more ground line so that current has a bigger ground path to flow back. That way is better for like noise interference, like eliminate the noise. Yeah.
Because the wires have a little bit of resistance.
Because it's like simply just because like it give you like instead of just flow all the current through a single wire, like it flows through like a much larger bundle. So again, like every wire, right? Like LDIDT will introduce a voltage, right? According to our physics, if you learned that already, right? So the magnetic flux change rate is induce the EMF. So basically, if you have the current change through a single wire too big, that's going to cause the magnetic field around it or induce the EMF around it. So that can act as a noise source or interference source for other neighboring signal. So you basically just want to make this, smaller. So that's a lot of times, you want to use a big, generous ground for most of the circuit board. That's the whole idea. Just, to eliminate the so-called EMI and EMF. What that means is the electromagnetic interference, or to eliminate the signal interference to other circuit. You understand? Because this generates noise. Yeah. So if you have a bigger ground, that will dissipate the current better. So you'll reduce that significantly. Is that clear, everyone? So this need to be, you need to be confident in the connection. If not, don't power it on. Because like I said, everybody just only have one board. So if you burn this thing, I'm sorry, I don't have any extra board to give to you. But then if you don't have any board, you're not going to be able to finish the semester. Understand? And hopefully, you can take this as a good practice to, for circuit building, and maybe, who knows, right? The side effect of this one will be later on your circuit, analysis or analog circuit, you can do much better in that course, right? So we'll see, okay? Okay, so Yeah, so I guess that answered a few like those questions. So is there any further question or comment regarding this the first homework? It shouldn't be that bad, okay? But then of course, the way of your implementation, you either just say, I will group all these things together, assign a value to it, without using your method saying, doing the bit masking and shifting. I'm okay with that. I really don't care that much about like how you implement it. As long as you get idea, that's fine. You understand? I don't require you to do exactly the same way as I would do it. So essentially then you say, what if I use a switch case structure? I would just say, okay, that it's not that elegant, but then it's fine for me. You understand? You could just do like, okay, switch case and then do a bunch of like 10 different cases. If that's what you decided to do, is fine. You understand? But I would prefer you do it like the way I mentioned in my class. Masking and then shifting and then basically just write a function. Let's see, group a bunch of function together. Lines together as initialize 7 segment, right? Those are basically enable the digital output, right? And then basically initialize those value, the data to high, for example, in this case, to turn off this 7 segment. And then that's initialize 7 segment. And then the second function could be, okay, display a number. So the input argument will be int n. So you just do this like a bit masking and shifting, right? This ping corresponds to this digit, right? So you end with a 0x40, shift to the right by whatever, 6, right? For example, that kind of thing. So essentially then in your main function, you could just have an array, right? A 10 element array, integer array, whatever this integer you write for display a digit of 0, which will correspond to 0x01, right? A digit of 1, which would correspond to a 4f, right? And so on and so forth. So you put into an array, and then you put in for loop for int I equals 0, I less than or equal to 9, I plus plus, right? And then whatever, display, 7 segment display function, data, square bracket I, and then that's it, delay for whatever, right? So the first one shouldn't be that bad. You probably just spent a majority of the time in building the circuit rather than writing the code, right? But then again, I think this is a good practice for you to get used to how to read the schematic and how to build a circuit. In terms of the coding part, it shouldn't be that difficult. Yeah. Any question, comments here? It should take about like 45 minutes to 1 hour. Yeah. It didn't take that long. Then that's better, right?
It took me in Blessing 6 hours.
Really? I don't believe you. Really?
No, that was till you told us
that
about.
knowledge.
That was till you told us that. Then we did it in like 15 hours.
The art pack in our kit.
Yeah.
And it's in the CM100.
Like, remember when they give you the electronic kit, they give you a piece of paper, like like summarizing a summary sheet, right? Basically, is the DIP package, like resistor. So that's the one. It also has a marking on top that says like 4116R. So it looks like a IC. It's not a resistor. It looks like a the DIP package IC, like this thing. Everybody, that's the RPAC. That's this thing. Yeah. So how many of you started already? Okay. So yeah, so for those of you who haven't started yet, pay attention to the data sheet, okay? And also like you may want to take picture or take note of this thing, because later you probably, if you haven't started, you probably don't know like what I was talking about here. So just pay attention to this, okay? Yeah.
Do you have to unscrew this part?
Yeah, in your like EOC kit, right? In your electronic kit, you have all the screwdriver, the long screwdriver. So you can use a screwdriver to open or close those connections. Yeah, this thing. Yeah. Like the jack. The jack has 2 leads coming out. He was asking like how we are going to be able to tighten this like connections. This thing here, and then you just use this like to tighten it.
You didn't label the first one.
Yeah.
Yeah, it's basically.
Is that clear, everyone? But of course, I assume you would be able to find screwdriver at home. If you cannot find this
I
one.
declined it.
Right?
I thought it was the same thing.
No.
Why did you send it to?
Okay, any more questions or comments before we move on to today's topic? We have some other things, more interesting, more fun things to do, okay? Yeah, blinking the LED take us 2 weeks, right? That's not acceptable. But anyway, so today we're going to talk about a new topic which is called interrupt, okay? So interrupt is a very important concept. So why do we need to use interrupt, right? Imagine, right, if you have, I guess everybody has the experience of going to a gas station, filling gas, right? So you go to the gas station, the first thing you do is you probably just, if you go to the Costco gas station, right, you insert your Costco membership, right? And then it says, okay, remove card quickly, right? You take it out. And then you will just go to a second screen says, you want to use a separate payment or not, right? Then you click on yes, and then okay. And then you tap your second payment. Now that's good. And then the next thing will be, select the gas type and start fueling, right?
Yeah.
So that's the typical process. You never go to a gas station, see something like this, okay? Welcome to the Costco gas station. Okay. Key in your Costco membership. Okay, give you 5 seconds. And then, okay, the next 5 seconds, okay, scan your credit card. Okay, give you 5 seconds. Next, give you 5 seconds to okay, start your gas type and start fueling. If you don't have time, let's see if I'm a very old dude, right? Cannot respond. If I cannot respond in that kind of thing, right, like a space, then I will be keep stuck in there. I need to okay, give me a few more seconds, but then this thing will be keep looping, right? So far, the code I have shown you is just in the while one loop. Everything just do okay in the sequence, and then come back again, and then do it in the same loop, right? So the issue with this is what? It's going to be if you keep doing this kind of the so-called polling, right? It's not like an interrupt mechanism. It's not building there. Everything will happen in sequence. You would have to allocate a time to it, right? So what's the disadvantage of this? Can anybody tell me why wouldn't I implement Costco's gas filling okay every 5 seconds? I keep welcome to the Costco gas station. Okay, key in your zip code, right? Okay, key in your membership. Okay, scan your credit card. Select the gas type. Start fueling. And then if this didn't happen, then go back to the initial while one loop and keep doing this. What's the disadvantage of doing that? Yeah.
Because you might miss your window you might miss a window in a certain step and then have to wait for it to come back around again.
Right. So it's just okay, it requires this guy will at least finish each action within 5 seconds, right? Mm-hmm. But then maybe he was doing this and then he forgot. Okay, the wallet is not in the pocket. It left in my backpack, right? So I need to go there, open the back of the trunk, and then when I come back, welcome to Costco, right? So I need to do this again and again, right? That's one thing. So what's the other problem?
If you do it quicker than 5 seconds, there's no response. You're just waiting for 5 seconds.
Right, even if you do it faster, you will still be held up there, right? That's another thing, waste a lot of people's time. If you're a young guy, right, you just get impatient, right? Yeah.
So what happens if we thought it worked, but it didn't actually work one of the times? And it was what's happening? It didn't confirm that yet.
Exactly. If you're if you somehow you key in one digit wrong, then you need to wait the whole cycle, repeat again, right? Yeah. This could happen, very likely happen, right? I mean, my zip code is 19711. Then what if I put 18711? Then it didn't work. I have to wait the whole cycle, right? Yeah. What's the other problem?
You're talking about propagation delays?
Huh?
You lose time for the transfer of data?
Not necessarily the propagation delay. I'm just saying okay, the whole design. If you design if you design your software that way, operate that way, what would be the limitation? What could be the issue? Like, it's not even like talking in the device level yet. This is not even the device. This is just more like a user interface design kind of thing. So what's the other issue?
It doesn't stop at all, like maybe it uses too much energy because it's always on.
Exactly, right? I mean, imagine if this is not Costco, imagine this is somewhere, I mean, of course, I don't have any kind of like a geographic discrimination against any state, right? But imagine if this is somewhere in the northern, North Dakota or these places, right? So, I mean, if you keep wasting this thing, this could be somewhere, you know, out of nowhere, a gas station. Maybe there's only 1 or 2 gas filling each month, and then you're just keep doing this loop, right? Spending a lot of money, spending a lot of money on utility, and right? Because like basically the idea is like if I have been idle for a long time, I could even like turn off my screen. I would not even doing this. Like, but now you keep requiring me to look this program 24/7, right? This is going to waste a lot of money, right? I mean, utility, you do pay for a utility. I mean, this electricity is not free. You cannot just like keep doing this like forever, right? So essentially, energy consumption is another thing. So we have all this disadvantage, right? So essentially, how can we handle that kind of thing? How can we make our microprocessor to attend to an event as quickly as possible, right? I mean, this is only one of this event. Let's see, there is another event, right? For example, okay, in this like a Ford assembly plant, a robot working alongside with a worker, but for whatever reason, right? There's a emergency condition happen, right? This guy is supposed to like press on this button, the emergency safety switch, right? Now this robot need to pause immediately, right? But then, you know, if you don't do that, you say, okay, the whole cycle is like, the normal condition is like, the robot will finish the complete swing, and then I will move a window, and then I pass it to him, right? And then robot will move and install somewhere else. But now there is a emergency condition. I need to make sure I'm not going to be hit by this robot in my head, right? And kill me. So I'm going to like press the button, and then this robot need to stop rather than say, no, I want to you know, swing, continue swing, and then next time I will check if somebody's press this button or not. Imagine, right? If I put in the while one loop, okay, if this button is not stopped, I'm going to swing, come back. If this button is stopped, you know, then I will stop. But the thing is like, in the while one loop, that check if this button is switched, right? Not necessarily happen exactly at the same time when you press it. But if you press it even like 1 millisecond later, you know, this check condition hold true. Therefore, the robot has to finish the whole swing, right? So this is another thing. Like, you also always want to make sure your processor is attending to an event immediately, right? You cannot just do this kind of the so-called polling, right? Polling wouldn't work, yeah?
That's the while loop, the whole.
Yeah, because like the ping polling is like, okay, you're just trying to check if it's true, do something. If it's not true, do something else. But then at the moment the check only happened that moment, right? Yes? So essentially this is another thing why we need interrupt. Interrupt basically give the processor a higher priority to attend to something. Once an event happens, it will basically say, I forget what I'm currently doing. I have to attend to that interrupt request, okay? So this is very different from in the real life, you know, situation. For example, okay, if I had a conversation with this guy on the phone, and this guy asked me for a question, he was interrupting my conversation. I typically would say, give me a second, stop talking to me, let me finish this conversation, right? That's the typical interrupt in real life. But in the microprocessor's case, right, interrupt always has highest priority. So basically, as soon as he interrupts our conversation, I have to listen to this first, and you know, listen to him first, rather than just like keep our conversation going. You understand? So interrupt has the higher priority compared to the typical process. While in our typical, you know, like everyday experience, you know, interrupt is actually not the highest priority, right? It's like, you know, your general task is the highest priority. So that's the only difference here, okay? So everybody understand why we need interrupt, right? Okay, good. So in this microprocessor, we have many different types of interrupt, and today we're going to be only focused on one type, which is called external interrupt. So external interrupt basically corresponding to some kind of external push button got pressed, okay, and whatever come out from the external input, okay. So this can be somebody press a button on an equipment. This can be a limit switch, there's a limit switch, essentially also a switch. When somebody press on it, or the limit switch mounted on the end of a translational stage, and when it reached the end, it got pressed. That switch got pressed, right? That kind of input, so that's called external interrupt. And we also have different type of interrupt, like timer interrupt. For example, we set a time, and then when time is running out, okay, goes to the upper limit as we set, it will do something. And there are many different interrupt sources, okay? And they call different vectors. And then the PIC32 is a very advanced microprocessor. It has 47, if I remember it correctly. But anyway, don't quote my number for that. So essentially, has tens of different sources, okay, including external interrupt, timer interrupt, ADC, event interrupt, serial communication interrupt, output compare interrupt, input capture interrupt, so a lot, okay. So of course, later on I'm going to talk about other interrupt source, but today we're going to be mainly focused on external interrupt, which basically means, like I said, okay, when the light is, below certain threshold, when somebody press a button, when this motor has already traveled to a certain range and then hit a limit switch, or when a piece of metal is present close to a inductive proximity switch, that kind of event, okay? So the interrupt can be triggered by either a rising edge, fallen edge, or both edges. So what that means is okay, if we configure our interrupt to listen to a rising edge, which basically requires a electrical level from a low to a high. Okay, so this low to high transition will trigger a positive edge. So essentially, when there's an electrical level from low to high happen on an external interrupt pin, and then this will be successfully trigger an interrupt. Similarly, the interrupt can be configured to be triggered at the fallen edge, or certain times can be on either edge, which means okay, if you press a button, right? Imagine, right? If I have 3.3 volt, and then I have a resistor, and then I have a push button and connect to ground, and then I put this signal into my microprocessor, one of the input pin, and use that as an external interrupt triggering source, right? So if I want to configure this kind of interrupt, what kind of edge should I have here? Should I configure this as a rising edge or a fallen edge? If every time I press the button, something will happen, then I will configure this as a
Rising. 'Cause you push
if
it,
I press it,
so you can.
it will be fallen edge, right? Because remember, if I, without pressing this guy, this electrical level stays as a high, yeah? 3.3 volt, yes? As soon as I press it, it's going to give me a 0 volt, yeah? But what if I said, okay, something will only happen, the microprocessor will only attend to this kind of external event at the time when I release the button. So that will be what? Rising edge, right? Because when I release the button, that means the electrical level will go back to high. Yeah? Right? Does that make sense? So the rising edge and fallen edge, basically, it's okay, when this will happen, when you want your microprocessor to do something, okay? So those are the rising or fallen edges. But then of course you say, can you configure them to whatever edge? Well, that's possible, but then certain times you don't want it the interrupt happen twice. Yeah? As case by case. What I meant is let's see if something happened, right? If this, if something press a button, you're supposed to like, okay, you're supposed to change the previous state. For example, this open will become a close, and toggle the previous state. So if I press the button, open will become close. But then, if I do like both edge trigger, when I release the button, then wouldn't this open again? So what's the use of that then, right? So essentially, but then there are certain cases you would want your interrupt to be triggered on either edge. But then, most of the time we'll just either do the rising edge or fallen edge. Understand? Okay. And then external interrupt. There are many different external interrupt sources, and some of this interrupt trigger source has a fixed pin assigned to it. For example, interrupt 0 actually has a pin assigned to that interrupt source, which means like the interrupt has to come from that specific pin, okay? But some of the other interrupt, okay, are remappable, reprogrammable, which means like you don't have a fixed pin assigned to it, but if you want to use certain input pin as that interrupt, you can configure it, okay? And I'm going to show you both, okay, today. So I will show you one example of like, okay, interrupt being assigned to a fixed pin, while another is interrupt can be remapped to a remappable pin. Again, if you remember what I said last time, the remappable pin typically have an R. You understand? Like for example, certain pin only have an RB. Certain pin only have a RB. For example, RB14. But then certain other pin can be called RPB14, which means this is a remappable pin. Remappable pin typically can be configured for certain extra functions rather than fixed function. But then that doesn't mean, okay, every remappable pin can be configured as an external interrupt. And I will show you the data sheet. There is a data sheet which is called like a digital I/O, remappable digital I/O table. And I'm going to show you a few examples later. But then for now, you just need to know certain pins, like interrupt 0, are bundled or tied to certain pin, while other function like interrupt can be configured to different remappable pin. The whole reason just because PIC32 is a very powerful microprocessor, allow us to reprogram or remap them, because otherwise if you assign every pin with a fixed functionality, if your project requires a lot different things, right, different pins, and you don't have much of flexibility of moving them around, then your microprocessor is going to be it's going to be very difficult to satisfy this requirement. But if we have certain pin which you can map to different functionality, then we'll make it more versatile, make it more adaptable to your more complex projects. Makes sense, right? So for example, let's see for certain application, I want to have the same port. I want to group the same port for a 7-segment display, simply just because when I write that port, write the code is one line rather than group different pin from different port together and then make the code difficult, right? So essentially, if I use a lot of those pins, then I don't have much of a choice of using the remaining. So if certain remaining pin can be remapped, then it will be good. But then if they all has a functionality tied to certain things, then it's going to be rigid. It's going to be difficult for me to assign pins, right? So edge polarity is remappable. That's what I said, or programmable. Basically, you will just do like EP, edge polarity assignment. So each individual interrupt can be separately or individually configured, which basically means, okay, interrupt 0 can be a rising edge, interrupt 2 can be a fallen edge, interrupt 3 can be triggered at either edge. So they're independent from each other, okay? And then the priority and sub-priority level are configurable. What that means is like, okay, what's the priority level? Even though you say interrupt has the highest priority, but then what if you have multiple interrupts? Even though that's very rare, but it does happen, right? Let's see, if I press this button, we'll do this. If I press that button, I will do that. But what if somebody like intentionally press 2 buttons together, right? Even though that kind of occurrence is rare, but then you still need to assign, then if both interrupt happen at the same time, or the trigger event happen at the same time, what kind of priority you need to assign to them, right? So this will be included as a priority level and sub-priority level. And those corresponds to two different register. So I'm going to talk about that too. So essentially, you just need to know, okay, those are the external interrupts. Some of the interrupts are built in with certain things. Some other interrupts are remappable. And the edge polarity can be programmed, and also the priority and sub-priority can be programmed. So what are the key registers here? The key register for external interrupt include the following: the IEC, okay, X. So this X is basically, a number, because like all these like registers are grouped into different registers, okay. But of course, I cannot, like if you quiz me and say, oh, what's the interrupt 0? What's the interrupt enable configuration register for that interrupt 0? Like tell me this X number. I cannot, okay? It's only the microchip, whoever invented this thing can tell you, but I do know where to find it, but I cannot memorize this like 1,000 pages data sheet, right? So it's not reasonable to ask people to say, tell me that, but you don't have to memorize that, okay? But anyway, they're grouped into the IEC, which means like if you want to set up an interrupt enable configuration register, you just need to do this belong to IEC register, okay? As far as which IEC, IEC 1, IEC 2, IEC 4, I don't know, but you just check, right? For example, if I want to do int 0 IE, which means like the interrupt enable bit for external interrupt 0, then I will just need to do like IEC something, like this number, bits, dot this. So I basically control F in my data sheet, int 0 IE, I will find this number. This is a 0, okay? Then I will do like IEC 0 bits dot int 0 IE. Understand? So let's say if I want to do a timer 2 interrupt enable, then I control F T2 IE, and then I figure out, okay, that belongs to IEC 2 bits dot T2 IE. Understand? So each interrupt enable is grouped into a different interrupt enable configuration register. So that you will have to look through the data sheet, and nobody can memorize those like 1,000 1,000 pages. Okay? Yeah.
I'm trying to search on the MC data sheet you gave.
No, it's not on that one. That one, like the data sheet, is only for the board. You need to search for the data sheet, which is the PIC 32 MZ 2048 EFM 144 data sheet. You want to find this data sheet.
Can you upload it with the other one?
Okay, sure. Let me just do it now.
Is it gonna beat that?
What's that?
No, there's only one.
The data sheet I posted there is only for the board. Those are two different things.
Who's gonna control that? Did the lab, you did the lab, actually.
I feel like
Should have did it, got in there.
Let me also put it under like course 0. Oh, it's not 1,000 pages. It's 760 pages. So that's better.
There's two VCCs. Is it from one side or the
Get the ground in there.
It's like a dictionary. Like it's a dictionary with
Technically, you should pick the message.
it doesn't say.
Okay, so everybody, the data sheet is under M1 course material. and then you go to M1 course material, right? You can see PIC32MZ 2048 data sheet is there, okay? Chip, can you confirm that if you can see it? What's that?
Yeah.
Like the PIC32MZ data sheet, that's the evaluation board. Maybe I will just rename it, just in case you misunderstood those two things. This is the evaluation board data sheet. Those are two different things. One is the microprocessor. One is the microprocessor data sheet. Can you look confused here? You don't understand what I meant? Like this PIC32MZ 2048 data sheet is the is the CPU. It's only the IC data sheet. While the other one I posted earlier, we call like a PIC32MZ data sheet. That's for the whole evaluation board. Those are two different things. Yeah.
Could you put that with the other one into the 0? Like the one
You mean
just
this
put?
here?
Can you put them next to each other?
Okay, sure. Then I will just drag it there.
Yeah.
So that's under the course 0. Under the course 0, okay, the course 0 introductory concept. One is the PIC32MZ evaluation board data sheet, okay? That has something to do with the whole board, like which pin is what. Understand? Versus the other one, PIC32MZ 2048 data sheet is only the IC, the square 144 pin CPU. Understand? Those are two different things.
So in 0,
I wouldn't be able to do anything.
Yeah. So let's see, right? Let's come here. If I look at the data sheet here, and then I say I want to find, right? What's the INT 0IE, right? So if I search, I probably need to download it in a PDF format. Okay. Okay, then I just do this thing here. Now it should be okay. Yeah. So if I do like int 0IE, I can see this belongs to IEC 0, right? I did remember it correctly. So, so like if you want to do like some other, right? Let's just try. Okay, how about instead of interrupt 0, I set as an interrupt 4, right? Or 3. So I do the same thing, interrupt 4IE, and then I will just click on Control F. You can see this also belongs to IEC 0. See that? Yes? Like this interrupt enable just one bit of a bigger register, but then this register IEC X, this X number can differ from 0, 1, or 2, 3. So essentially nobody would be able to memorize this, right? So you go to this data sheet and then control INT0IE, you will be able to see IEC 0, yeah? Is that clear, everyone? Because we have many different interrupt. Like I said, output capture, input capture, timer interrupt, and within each output and input, you have also like output capture, you have 6 interrupt sources. Input capture, another 6. Timer, 6. Right? And so on and so forth. So you have many different interrupt sources. They belong to different places. Okay?
Somebody write this by hand?
What's that?
Somebody make this by hand?
I think so. I mean, the original people who make this like architecture, they have to, because this is their invention. They have to like plan ahead of time, like which register I will use for what. Yeah.
Fascinating.
Huh?
Oh, it's pretty cool. Pretty cool.
Well, the company didn't pay them for no reason, right? Right?
Wait, that is possible.
Because like once they determine this, company can just print out this thing, every piece, $9 something. Every year they print like millions and millions of this thing out, right? I mean, it's just like printing money, essentially. Look at all this big company, Broadcom, right? Like NVIDIA, their profit margin is more than 50%. So essentially they keep printing out money, but who decides this kind of architecture, right? Those people who invent this one will define the rule, but of course those people get paid. So you say, yeah, this is tedious, but then you get paid that $1 million, right? So you, of course, you need to do this.
You started the intern.
Shit, for that money, yeah.
Huh?
For the right amount, yeah.
You can't trust the interns.
Intern do this? Okay. I mean, if you really have that kind of intern, you will be nice. I mean, the company will be very happy, right? Yeah.
Engineers are scared of writing stuff, so.
The designers plan it and the intern takes the last one.
Okay, is this clear, everyone?
Yes.
Right? So let's see. If I want to do like an ADC, right? If I want to do like an ADC data 15 interrupt, like basically if I have an ADC channel on the ADC channel 15, if there is any kind of A to D conversion happening, I want to set an interrupt enable bit. Okay, tell me which one that corresponds to. ADC data 15. So you will say, okay, I will do control F, A, D, C, D, 15 IE. I see this belongs to IEC2. Therefore, I just do an IEC2 bit start, AC, AD, CD, 15 IE equal 1. Basically, I enable that interrupt. IE means interrupt enable.
Wait, say the order again.
What's that?
The order, you just said it. You said ODE, I mean OOE.
Like IEC2.
Oh.
This is the word, right? This is the word. This contains 32 bits. Each bit represents a different interrupt enable. You do IEC2, which is the bigger one, bits dot ADCD 15 IE. Oh, by the way, where's Angel?
She told you she wasn't gonna be here.
Huh?
Remember? She told you she wasn't gonna be here.
Okay. Then she will fail next time for the quiz, I guess. Let's see. Do we have everybody here? Make sure.
Do you have a question?
Oh, let's see. 1, 2, 3, 4, 5, 6,
Is there a quiz today?
Yeah.
No,
6.
should be fine.
Okay, so we only missing one person here. Okay, is that clear, everyone? Yes, right? So interrupt enable is one of the bit, and then next time, right? Anything has something to do with the board. Look at the other data sheet. Anything has to do with the configuration register or the CPU. Look at this data sheet. Those two things are different. Understand? Yeah. One is about the product. One's about the only one component. Yeah. Yeah. Okay. So this is one of the source, right? So this is the interrupt enable. How about the interrupt flag? So the interrupt flag, first of all, like what's an interrupt flag, right? Interrupt flag is okay, what's the interrupt flag? Interrupt flag is it's basically just a status indicator. Let's see. Let's make an analogy to like the flag on your like mailbox, right? So essentially, every time if you have something to mail out, you will set the flag on your mailbox so that when the postman come to deliver a mail to your home, it sees this flag and basically knows, okay, then I probably need to pay attention to see what's inside. This guy must have something for me to bring to the post office, yeah? So that flag will be set, right? But then when he took your stuff, he will reset, he will clear the flag, yes? Because he basically says, okay, I took it out. So, so maybe like, when it was snowing or maybe there's like a rain heavily, you don't have to go there to check if this guy has already done this for you, right? Because if you see that from the window, oh, okay, it's set, it's clear. That means I don't have to take out the stuff and then drive to the post office the next morning, yeah? I know the postman took care of it. Same idea, okay? Interrupt flag in this case is basically says, okay, I set the flag, okay? I clear the flag, basically says, I have already taken care of the previous interrupt event. But then if something happened, if the interrupt event happened, right? This flag will be automatically set, you understand? So essentially, only when this interrupt event got cleared, got handled, in this case, the mail piece got taken out by the postman, it will just clear this flag again. So that next time, when another postman, let's see, okay, there's a morning guy, there's an afternoon guy. So the afternoon guy come here, if see this flag is cleared, he will not be reaching into the box to see something. But if it's not cleared, he will just reach the box and do something there, right? So this flag basically means, okay, whether this interrupt event has been taken care of, okay? So in order for you to set up the interrupt property, you have to first clear it. Understand? If it put in the 1, basically means, okay, this interrupt has already been taken care of. I don't need to care. The microprocessor basically, if you see the 1, basically says this has been taken care of. I don't need to do anything. But of course, you say, didn't you tell me, like, okay, you said the flag means like, okay, the mailman need to take care of it? How come this is different? Yeah, this is a different case. This basically says 1 means like, case has been taken care of. 0 means it hasn't been taken care of. You understand?
So 1 means resolved.
1 means resolved. So every time, in order for you to configure the interrupt property, you have to first clear the interrupt. You understand? Because otherwise it says, it's been taken care of, I don't need to do anything. So at the beginning or at the end of each interrupt event handling, you want to clear the interrupt manually, yeah.
You also just check the value to know if it happened right?
You don't need to check the value. Like it's typically just like you need to manually clear, because every time once you get into the interrupt, they'll execute the stuff and then you just clear it basically. So next time when the same event happens, it go to this interrupt function and do whatever inside. But if you don't manually clear it, okay, once it jump into the interrupt and then it come back and then that flag has already been set to 1. The next time when somebody presses this button crazy or even damage the button, it's not going to do anything because it says has already been taken care of. I know you want me to pay attention to this interrupt event, but before I execute this interrupt, I need to check whether it has been already taken care of. So since I have already constantly CO1, means like, okay, I know it has been taken care of, therefore, I'm not going to do anything.
So like maybe you could set 1 button to interrupt and then the other button to clear. So you could spam the first button and then like.
It's typically just handled at the same button event, like inside, at end of the interrupt, before return back, it will just clear it. But anyway, I will show you an example. You have a better understanding later. So you just need to know this is the status, interrupt status, and same thing if you want to find, okay, an int0if. Control F in the data sheet, int0if, to see what number this x is. This x represents a numerical number, but then of course it could most likely be a 0. But anyway, you just check. Understand? So, in order for interrupt to happen, you have to clear it. Okay, and then the next one, IPC. Okay, as the name suggests, is the priority. Okay, so this is the interrupt priority control register. What that means is like, okay, we say every event, right, has a higher priority compared to the normal operation of the microprocessor. But then since we also have tens of different interrupt triggering source, right? What if 2 things happen at the same time, right? Because they both have high priority, and then which one has a higher priority, right? Just like say, okay, now we're having a conversation. This guy interrupt me, and this guy interrupt us too. So now, we need to now interrupt our conversation and attend to this 2 guy. But which one is the boss, right? So essentially, the boss will have higher priority, 7, and this guy says, okay, 5. Let's see. Sorry for a moment. So you're a 7, you're a 5, right? Then I will look at those 2 things and say, okay, I will attend to the boss command first, and then I will listen to this guy, with a lower rank, right? This is unfortunately, always the case, right? So listen to the boss first, and boss say, okay, do this. I finish that, and then I come back to you, okay? You said do that, and finish that, and then I go back to normal. What did I say? And then say, okay, we finished here. Okay, let's continue our conversation. Just like that, okay? Right? Make sense, everyone? So those are the priorities. So priority has a numerical setting from all the way from 1 to 7. And 7 being the highest, and 1 is the lowest. You understand? But of course, can you set them as both 7? If you set them both 7, then basically, you didn't assign manually add interrupt to them. Therefore, the interrupt priority will be determined by a predetermined vector table. Certain interrupt has higher natural priority compared to the other, which basically says, okay, if you don't want to assign who is your boss, right? The boss there's a default ranking of the boss. You understand? But can you change the boss order? Yes, you can. This is the perfect chance for you to change their natural order, right? For example, this guy, by the ranking, this is 7, this is 5. But you say, no, I want to set this guy 7, this guy 5. Can I do that? Of course, you can. But if you set them as both 7, right? Like you just lazy or you're not sure about it, right? Then you just say, okay, how about I set them both 7? Then they will look at the intrinsic order. They say, okay, I know this guy is higher than this guy. Therefore, when both of this interrupt happen, I will attend to the boss first and then this guy, right? Next time I make you the boss, okay? Don't feel unhappy. So, is that clear, everyone? Okay, very good. And then the next one, the intcon. Intcon is the first register, and this basically says global interrupt configuration. What does that mean? It's okay, in order for interrupt to take event, right? Particularly when you have multiple interrupt event, you want to set an intercon. So this intercon basically says, okay, I will globally enable all the interrupt. You understand? Because this is the individual interrupt enabler. This is the global interrupt enabler. Understand? So you will need for every interrupt to happen or to be configured properly, you need to configure all those 4 interrupt sources or the interrupt register. Okay? Is there any question here? Okay, so let's move on to the next slide. So what are the configuration steps, right? We need to configure first of all, if this is the interrupt, naturally we need to configure this is the input or output, right? So Michael, if I want to configure a button press as an interrupt triggering event, right? So that button, the wire the button connected to is an input to the microprocessor or output to the microprocessor? Input, right? Because I want to check the electrical level changes. It's not like, okay, the microprocessor want to output something there. It's actually scanning the input status, yeah? So it's the input. So you need to configure the corresponding pin as the digital input. That's the first thing, right? So of course, certain pin has the dual functionality, right? It can be an analog input or digital input. So in order to configure those pins as external interrupt, what should you do? You need to disable the analog, yeah? Right? Remember certain pin has the AN something in front of it? So putting this okay, the trace as a 1 is not sufficient. You need to also do an AN select B bit.ANSB14 equals 0. Disable the analog input, yeah? Right? Don't forget about that because otherwise it's not going to work, okay? And then configure the edge polarity through the intercon register because you need to know okay, whether I want to trigger this event on the rising edge or the fallen edge. For example, if I press a button, if this button is pulled up to the 3.3 volt by a pull-up resistor, that means as soon as I press the button, I change the electric level from high to low. So therefore, the fallen edge will be my edge polarity. But on the other hand, if I say, okay, I will hold this button there, as soon as I release the button, something will happen, then you will set this as a rising edge trigger, yeah? So edge polarity is application dependent. There's no general rule. It all depends on if you want, if you want this person hold on this button and then say, now if you release this button, the bomb is going to blow up, right? Therefore, you have to trigger it a different way, yeah? Right? So let's say, okay, I'm holding this button here, I'm giving a constant low, but the moment I release my hand, and then it was just low to high, therefore, it's rising edge trigger the bomb, right? You cannot do a fallen edge, yeah? Why you laugh? I mean, this is one of the perfect application here. So, no, this can make a perfect bomb. What do you mean? You cannot trust this. This is very trustworthy. Okay. I mean, this is more than adequate for the bomb. It's 100% trustworthy. Yeah. Okay. So the next one, right? So set a priority and sub-priority. Like I said, this is when you have multiple triggering source, you want to set a priority. Like, even though you say, okay, what's the chance, of those two different interrupt events happen exactly at the same time? Well, for like a simple project, it's happened very rarely. But imagine if you have many different triggering sources, right? Like the microprocessor got constantly interrupted by so many different sources. In that case, you do need to worry about, if two or more events happen at the same time, which one you want to attend to first, because it will give you different results, right? So those are the priority setting, and then again, those are application dependent. There's no general rule. This is always depends on, like, okay, how you define different triggering event, like what the corresponding action you need to take, okay? And then the next one, enable the interrupt, of course, clear the interrupt flag, right? And then write the interrupt subservice routine. So this interrupt subservice routine is not a function, okay? It's not the callable function, which means like you cannot call this interrupt service routine, right? Function it's like, okay, whatever you can call in main, right? But this interrupt subservice routine even write like a function, but you cannot call the function. This only happens when the corresponding event happens. You understand? So interrupt service routine can never be called, right? Because it's not a function. It's something just like say, okay, if something happened, corresponding block, corresponding subservice routine is going to be executed. But if this thing never happened, you cannot in the main function call an interrupt subservice routine. Understand? So this interrupt subservice routine is actually what you want to do, right? For example, if I release my hand here, right? Now, at the time I release my hand, if this interrupt was configured properly, the microprocessor will stop what it's currently doing. It may be somewhere in the while one loop, right? It doesn't matter where it's in the while one loop. It quickly jump into the ISR, the interrupt subservice routine, right? It says, now, go to this subservice routine, now have a countdown, right? Display on 7 segment, okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, right? And at the same time, let you input your diffuse code or whatever, a password, right? One time, right? And then if it unlocked properly, okay, nothing happened. If it didn't unlock properly, then ignite or whatever, right? Then and then it will be too late, yeah? So essentially the ISR will be just for that. But of course, I'm not encouraging you to make any kind of terrorist activity here, okay? I'm just talking about the potential application scenario, okay? Understand? Because I don't want to be visited by somebody saying, okay, yeah, you let people do something here. No, I don't meant anything here. I was just talking about a possible application scenario, right? Okay, so write ISR. So this is the ISR, it's the interrupt subservice routine. It's what, when something happens, when this interrupt event happens, this is the task, it's going to the corresponding task. You understand? So what's the typical process? The typical process is like, okay, the microprocessor will keep executing line by line. This is our main function. And then this is this line, and then this is the while one. And then they'll hold in this while one, and this line, this line, this line. But then somebody press a button, and then this will quickly go to the ISR, the interrupt subservice routine, and finish whatever there, and then come back to left off. So this is like how interrupt happen. You understand? So when this thing come back, it's not going back to the first line of the main anymore. It's going to be where it left off. You understand? So the process inside the microprocessor is it will store its program counter, like where it left off, in a memory location. Basically memorize, okay, where we left off. It's just like, okay, when we have the conversation, before I attend to the boss interrupt event, I remember, okay, we were talking about today's weather, whether it's good for fishing or not, right? So I remember that topic, right? And then it's like, what do you need, right? And then you say, okay, go get me a cup of water, okay? Get you the cup of water. Okay, here you are, sir. Okay, do you think tomorrow is going to be a good time for fishing? Right, so we keep going, yeah. Is that clear, everyone?
Yeah.
Yes.
So would you say that maybe at the end of the ISR, you should have it like reset the flag?
Clear the flag. That's always
Like
the,
at the end of the ISR?
right. Because, you know, at the end of the ISR, it's like when everything happened, and then the clear of the flag bits equal 0, the interrupt flag bits equal 0, basically ensure next time when boss interrupt me again, I'm going to attend to him. Because without clear this interrupt flag, then basically, okay, next time he was saying something, I just first check, you know, like I set this flag here, I put this flag pole here, right? Basically means like I have already taken care of this guy. Don't bother me anymore. I'm not going to talk because I know I have already did what you asked me to do, right? I passed you a cup of water. I remember that. I didn't clear that. You understand?
Mm-hmm.
But then if I clear that, next time, okay, when we talk and then he interrupt, I say, what do you need? Right? Okay, I get you another cup of water. Does that make sense?
Yeah.
Okay.
So that's it.
Yeah.
So when you call, like whenever the interrupt is enabled, does it automatically set the flag, or do you have to call take the interrupt and then set the flag in the code itself?
Just like when the interrupt sub-service routine finish executing whatever inside this routine, like the machine physically, it will set the flag.
Okay.
So you manually clear the flag. You force it to say, okay, listen to his command one more time. But then when the interrupt service routine got executed, it intentionally just set that flag. Basically says this time this command has already been taken. But then you need to clear it so that next time this guy interrupt our conversation again, I can attend to him. Otherwise I won't, because every time before I decided whether I need to attend to this, go to this interrupt service routine, I will quickly check whether this flag has been set. If it's set by the system, right? So if nobody clear it and I saw, okay, it's set, therefore, don't bug me. I gave you that cup of water already. I'm not going to do it, right? But then if I clear that, basically means, okay, what do you need, right? So essentially that's very important. You need to manually clear it at the end of it. But you ask the right question is like, okay, where did this flag got set? The flag got set automatically by the program.
Okay.
You understand? Once it finished, once it jumped out of this interrupt service routine, if you don't do this, the end of it will be just setting it too high. Yeah. Machine set it high. Machine basically says, I did this. But then you say, forget about this. When he asks you to do this again, come back. So this is where manually you need to manually clear it. But now, of course, if you say, if this is such a routine, then why you bother? Why this like the inventor of this guy who got just paid $1 million wouldn't directly write this clear automatically clear for you? But there are certain cases, okay? You only want your microprocessor attend to it once, not always. Understand? Makes sense, right? Yeah.
Maybe like an emergency thing, like one and one off.
Yeah, like for example, like one shot, right? Like for example, some like a satellite you send to the outer space. When something happened, you know, you only like, okay, retry something once. You're not going to constantly retry that thing, right? So you only need it once, yeah. So yeah. So yeah, so that's the case here. Is there any question here? No, right? Okay. So.
It's the previous one.
Why is going back?
Needs calibration probably.
Okay.
Smartphones are needed.
Okay, so next one. The next one I'm going to do an example. Let's take a break here. And then when we come back, I will do an example. Let's just do one example here. Okay, so let's see. The example here would be like I want to press a button and then toggle an LED. What that means is like, okay, I want this to do something, but then I want to like every time I press a button, it will toggle an LED display. Okay. Like I'm not using the polling method anymore. I'm going to use an interrupt method. Okay. So let's just do that, right? So let's just start a project. Let's just start the project again from the beginning. Let's. What's that? Yeah, we're going to need to use the board. So make sure you just take the board and also your breadboard out, and then let's just follow along, okay? Make sure you understand, because your homework is going to be a lot harder than this. So it's probably a good idea to follow along in the class, okay? So, so let's just start a new project. Let me close this project and then let's start it one more time. But next time I'm not going to start from beginning again, okay? And this is the last time I'm going to show this start from scratch. Okay, so we open the MPLAB XIDE, new project, and then standalone project, and then next. And then PIC32 family, and then PIC32 MZ2048 EFM 144, and then the tool. If I connect this tool through the USB cable, you should see that serial number. Otherwise, double check your USB cable. Sometimes you need to like unplug and plug it again. And I probably need to go back again, because like generally like if I plug later, it's not going to be recognizing it. So I need to go back to this like 32-bit and then typing this one more time. And then, wait, where is it?
Pretty good with my stuff here.
Actually, no, yesterday I didn't think outside and close out, but when I opened it back, I was different.
I've had to clean it and build it again.
Usually, when I go to if I close it, and it asks me to save the project, and I hit save, so I gotta shut it off. Like I literally have to force power it off for this previous.
Complete bits. Oh, that.
Well, I created it. I don't know if it crashed or if it just throws me on a new tab, but
I had done that.
I'm used to that right now.
So I never knew you.
Okay, finally. Go to the next one, XC32 compiler. And then this will just do like, okay, interrupt, for example. If I name this as interrupt.
Yeah, someone said it was right.
And then I come here, right? I will just add that header file here, which is the config underlying bits. Oh, wait a second. I name it differently. I want to name it the configure underscore bits. And then Control A, Control X. And then remember that configure bits, right? You actually can generate from this thing. Okay, set configuration bits, and then get source code, and then Control A, Control C, and then put it here, right? This is essentially the auto-generated code. And like I said, as a personal preference, I always like put this like include in. Crop the last line, and then put into the source code the first few lines for the header. So in this source code, I'm going to create a main file. So I will include the PIC32 header here. Okay, and then I will also include the config bits here. I would also need to include a system attributes. Attributes. Wait a second.
Ours is attributes.h.
It's not this one. It's what?
Attributes.h.
ATT
ATTRIBS.h.
And then
R
second
IBS.
I
Isn't it 4x's?
V
No, B.
B S
Dot
Yeah,
H.
it's 4.
dot H.
Yeah.
Like for some of you, like you're actually like your compiler, your IDE can actually like auto complete.
Yeah,
You know, like
mine,
once you type in this one, it will give you that.
The top-
Unfortunately, mine is for whatever reason it's not doing that.
The top one is 4x.
Yeah, so mine is not doing this. So you know, it's harder for me to remember. So I don't remember. I only know this is system attributes. So what that means, right? Like this is the third one. The first one is the PIC32 microcontroller header library. The second one is the cross C platform header. And then the third one is the configuration bits local folder. And then the last one is the system attributes. And this system attributes is a needed header if you want to use the interrupt subservice routine. Because later if you do like a double underscore IRS, like interrupt subservice, ISR, it's not going to be recognizable if you don't include this header. You understand? Because like they will say like, what do you mean? Like if you do like a system level of 7, I don't really know what system level of 7 means. Understand? So let's also go to our D2L. I believe I have some code, you know, like a sample code for you, but this right on a different microprocessor, and I want you to open that one, and then you know we're going to configure it for the current use. Okay? Let's just do it together. Okay, so that's under the course 3 interrupt, and then you can download, okay, one of those two things. Let's just do interrupt 2, okay, let's see what that is. Hopefully that's not the SpongeBob thing. Okay, that's not SpongeBob, that's good. So let's just take this thing, okay, let's just Control A, Control C this thing here. And then goes to this one, the main Control A, Control V. And then again, let me explain them line by line here. So the top 4 header I have already explained, okay? And then I have 2 global variables. One's called count, and the other one is a flag. So the count will count how many times I press a button, and then the flag is basically, you know, like a global variable. I want to indicate the flag status, okay? So the void delay function, again, is a empty delay, is a nested loop delay. And then I'm going to talk about the remaining thing here, okay? So you can see, starting from 18 to line 24, there is a interrupt subservice routine, right? So the first one, and then the second one. The first one is a number, okay? The second one is a interrupt priority level, okay? And then this is using a timer 3 as the interrupt. But we're not using a timer 3 as an interrupt here, okay? I'm going to first talk about the interrupt 0, okay? Right? So let's just do a interrupt 0 here. So in order to initialize that interrupt, let's just say, okay, what's the interrupt 0? Let's just go to this data sheet of the board, right? This is the evaluation board data sheet. So let's just look at the schematic for interrupt. So let's see schematic. So let's look at JTROL. JTROL interrupt 0 is pin 11, has a INT 0, RD 0, right? Let me just first do one example by setting an interrupt to interrupt 0, okay? So what do I need to do is like, I need to connect a push button. You guys must have a push button in your box, right? Do you?
Yeah.
No? If not, that's fine. Let's just use the onboard push button then. Like we're using the onboard push button. We're using the onboard push button, everyone. So let's use the switch 3. Switch 3, remember? The switch 3 is the RB14, yes? And then this side connected to ground, yeah? Right? So I want you to connect this to 3.3 volt and then 1 kilo ohm resistor. And then I want you to connect this one to an interrupt 0. Or maybe this is not very clear. Let me draw it in a professional way. Okay, 3.3 volt, 1 kilo ohm, push button and ground. And then this is the place. Okay, and then connect that one to interrupt 0. Remember, this is also a RB14, yeah? If you refer to the data sheet later, or I scroll it down here. Okay, I scroll down because it's right here. Yeah, here. See that? RB14 here? Yes? RB14? So this is where this S3 switch is connected to. So I'm basically using the S3 switch as the external trigger source for my external interrupt. Does that make sense, everyone? So let me connect the circuit physically. So let me unplug everything else so that you can have a better view.
That's the first one. No, that's the first one.
What's that?
First pin. Oh. Where you get?
Literally the same thing.
I don't care.
So you can, if you know how to connect it already, then connect it. Otherwise, I will show it here.
Yes.
Where's the
That's all it matters. It's just like that one, basically.
So, okay. So here. Let me rotate this one by 90 degrees. Okay. So you can see that this is 1 kilo ohm resistor here, right? The 1 kilo ohm. And then we have like one side goes to this 1 kilo ohm, the other side come back here, right? Okay, so let's see. One side goes to the 3.3 volt, right? The other side goes to what? The RB14, remember?
Yeah.
So, right, if we go to the original data sheet, you can see that, okay, 3.3 volt was the pin, what, pin 10, right?
10, yes.
If I remember it correctly, that's the pin 10 on J12.
Wait.
That's
3.3
RB14 is pin 10.
Huh?
Pin
Pin
1
one.
is 3.3.
Oh, pin 1, yeah, this one.
Yeah.
It's written here, that's right. So it's the pin 1, right?
Yeah.
So you connect pin 1 to one side of the 1 kilo ohm resistor, yeah?
Yeah.
And then you connect RB14, like you short a wire from like female to female, and then you connect it to the pin 10, right? Yeah, RB14, yes?
Yeah.
Connect it here, right? Short a wire there, and then connect a wire from 11 to the other side of 1 kilo ohm. Is that clear, everyone?
Wait, how can we connect if there's something on it?
What's that?
So you gotta do
3.3 to the resistor. Yeah. And then
Okay, let me make the connection. Okay, so
What did I do? What did you do? You just whipped them and said, "Do that."
and like let's first like unplug the cable. Make sure we're not going to do any kind of hot plugging or unplugging. Unplug the cable first, okay? Yeah? Okay. So I guess I lost the
That's why,
customer, that's bad. Okay. So I want more customer, guys, referral. So let's see. Let's see, we have a
There you go.
let's see, this is 1, right? The right hand side 1 is a 3.3 volt. So I'm going to connect this guy. I need a male to female. So okay, I'm going to connect this one here. So this is going to this guy, okay? The top of it, right?
Yeah.
Then the bottom of it, that need to be going to that pin 10 thing, right?
Yeah.
Pin 10, okay? So I need another male to female. Honestly, I think so far it's not that bad. You disagree, folks?
Yeah.
Okay, good. You disagree. So that means I'm going to lose another customer.
Oh,
So, yeah, I don't like that, okay? I think it's pretty, it's very light for now. I mean, if you don't like it now, and then you won't like it later. So, let's see, okay, we connect this guy here to another, like anywhere we want, because we only have one precious pin, right? Going back to 10 and 11, right? So basically, we're going to connect this guy to 10, 2, 4, 6, 8, 10. Yeah, this is the 10. We also need to use another male to female, goes to 11. Does that make sense to everyone? I hope it does. So 1, 3, 1, 3, 1, 3, 5, 7, 9. Yeah. 1, 3, 5, 7, 9, 11. Yes. Does that make sense? Let me focus it better here. So you see, I'm connecting this guy to 3.3 volts. So this goes to your pin 1 of the board. Pin 1, that's 3.3 volt. This is a 1 kilo ohm resistor. I'm using this guy to basically just loop it to connect it to another, like basically here, bring this node here. So I connect 1 to 10 and 1 to 11 basically. So make them to the same node.
Do we need a ground, or is ground taken care of by the?
No need for the ground. Ground is on the board. I mean, of course, this is like, originally if we have evaluation board, we don't need to do this. But unfortunately, we don't have it, so we need to make the circuit.
This was a yellow one.
But I guess it's not too bad. I gave you more practice on circuit building. Yeah. Is this good? Clear, right?
Can you explain it again?
No?
Can you explain it again?
This side goes to pin 1, 3.3 volt.
Yeah.
Yeah.
Pass through this guy, 1 kilo ohm resistor. The other side goes to this temporary location. One of the pin goes from the same location to 10, which is your RB14, which is the push button. The other one goes to 11, which means also you're sending whatever this signal on this RB14 to the external interrupt source,
That makes sense.
RD0. Does that make sense?
Yeah.
Yes, right?
I get what you're doing.
Yes? Yes or no? Yes, right? Everybody made that connection?
No.
No?
Not yet.
Do you know what the timing wires?
No, don't know.
Then follow along. Okay, one more time. This guy, pin 1.
Pin 1.
This guy, put another wire male to male, goes to whatever row, a different row.
Okay.
And then from that, the same row, go to 10, go to 11. Yeah. Clear, right? Okay, let's just write the code then.
Oh my
Okay, so let's write the code here. So how do we do that, right? The first thing we need to do is like, okay, we want to say, we want to do what? We want to make the RD0 an input, yes? So that's a trace D bits dot trace D0 equal an input 1, yeah? So what's the other things we need to set the interrupt O1? What are the 4 registers we want to do? Like interrupt enable, interrupt flag, interrupt priority, and intercom, like global interrupt enable, yes? Right? Yeah. So let's just do it in that order. So we can delete the next 2 lines of code in the original like a sample, which is using like a T3, right? So let's see, what's the interrupt flag in our case? We're using interrupt 0, yes? So we need to go to the data sheet of the PIC32 data sheet, right? We need to control F for int 0, right? IF. Oh, I need to download that thing again. Or maybe like it's in my download folder. Yeah. So I will just like control F, right? The first one I need to get is what? INT 0 IF, right? Interrupt flag. Yeah, that belongs to what? IFS 0, yes? So let's just write it down, IFS 0. Or maybe we hop back and forth anyway. So let's see. Okay, IFS 0 bits dot int 0, right? IF equals 0. This means what? We're clearing. In order for interrupt to take effect, we need to first clear the interrupt flag, yeah? So what's the next thing we need to do? It's the interrupt priority, right? INT 0 IP. So let's set it to a 7. Okay? So let's just do INT 0 IP, and then we say, okay, that belongs to IPC 0, right? Therefore, we also do IPC 0, right? IP, yes? So the next thing is the INT 0 IE, interrupt enable. And we search it again, and we found out it's actually under the IEC 0 bits, right? So it's IEC 0 bits, INT IE. And of course, we say we want to set this as the highest priority, which is 7, okay? Now the intercom, right? Intercom is the global interrupt enable, and also will configure the interrupt priority, the edge polarity, remember? Right? So let's just do the intercom, search for intercom. So you can see, all those bits are not enabled except the MVEC. This bit means like multiple vector of interrupt enable. So when you have multiple interrupt enable, you set this bit as a high. Otherwise, you don't need to care about it. Understand? This one, right? And then all the other things are the interrupt edge polarity. 0 represents a high to low transition. 1 represents a low to high transition. If I remember it correctly. But then of course you say, I need to check, right? If you check it here, you say, it says, okay, where is it? Here, yeah. So 1 is a rising edge, 0 is a fallen edge, right? So do we need to, if we press the button, we want to trigger the interrupt immediately, what kind of edge we need to set? Fallen edge, yeah? Because we have a pull up resistor. Normally, without pressing the button, we have a high, right? Yeah. When we press it, it has a low, yes? So it's a fallen edge, which means we need to set it as a 0, yes? So the intercom, the setting here, we have here was like 1004. But who cares? Because this 4 is not the lowest bit. That's some other interrupt. So we could also set this as 1000. Yeah? Which means like we're enabling a multi-vector, which means like multiple sources of interrupt. Even though we're only using 1, but you still can put multiple here. Doesn't really matter. and then ASM, assembly EI, enable interrupt, okay? And then the T3 count, we don't need to care because we're not using the timer, so we can delete that timer. So this is how we're going to initialize our interrupt. So the first step is set this as a input. Clear the interrupt flag, set interrupt priority, and enable the interrupt. And set the edge polarity, and then globally enable all the interrupt. Even though we only have a single interrupt, we'll just do it this way. This is a typical template. Does that make sense, everyone? Yes? Okay. Did our customer leave the box back here or no? No?
There's no box there.
Huh? No?
No box.
This is mine.
Oh, okay. Yeah, then probably in that case I need to remind him because I don't want people to leave the class without returning the state property, right? Okay, so yeah, so that's the enabling process. Is that clear, everyone?
Yeah.
Configuration for interrupt. Yeah? Okay. Okay, so if there are no questions, then let's talk about this interrupt subservice routine. Remember, so this is enable, and then this is the while one loop. You can do whatever you want here. This is really doesn't matter because for now we just make it stuck into an empty while one loop. Once it finishes the initialization, go into the while one loop and do nothing, right? But then every time when we press a button, we want this guy to come to the interrupt subservice routine. So now let's figure out just two things. What are those? The first thing is the interrupt vector number, and the second thing is the system priority interrupt priority level. This is the system assigned priority level because we have already included the system attribute. This is one of the system attribute defined. So essentially 5 means like system level, like a priority level of 5, but you can set it as a 7, IPL 7 SRS. And this is the interrupt subservice routine name. As long as it has a distinct name, it doesn't really matter because every time the microprocessor jump to which vector, it depends on the vector number. It doesn't really care about this name as long as this name is differentiable from each other. You can call this dog, cat, whatever. But of course, for readability of the code, you don't really want to give it a dog, grandma, whatever, right? So you basically need to still make it readable to others. Even though microprocessor didn't jump into this subservice routine based on the name, it's actually based on this number. Okay? Every interrupt triggering source has a vector number. Okay? So now let's figure out what's the number here, right? Because we're not using the timer 3 interrupt anymore. We're using a interrupt 0 vector number. So again, you go to this data sheet, right? And then you do Control F, and then interrupt vector table. Yeah, it's here on 7.2, which is on page 130. And then there's a interrupt table, right? So these are the interrupt table, and we need to put a number there, vector number there, okay? So you can see original timer 3 has a they change it, okay. So they change the vector name. So essentially, we will just either by building a number, vector number, like in the old data sheet, right? They give you the IRQ number. They also give you the vector number. But in the new table data sheet, they don't have this number, vector numbers. But they do have this name, vector name for it. Like XC32 compiler, they give you this vector name. So we can find which is interrupt 0, right? External interrupt 0. you can just directly do like external 0 vector. So you replace this one instead of a number. Okay, so you can just do replace it with the external vector. Like this is the vector, which is external. What's the name? Full name of it?
0
External
underscore 0
underscore 0 underscore vector, right?
Yeah.
0 underscore vector, and then you do a 7, and then you change this guy's name as int0 interrupt. Okay, and then all this interrupt routine should have no input argument because it does not require any input. You understand? This is only a system event triggered, so there should be no input argument. Okay, is this clear, everyone? And then now, here I just increment the count, but of course, the count is a global variable. I just every time, like, how many times I'm pressing it. Let's imagine later, the project bigger. I use a 7-segment display. I press it, and then I want to 1, 2, 3, 4, 5, right? I can display the counting number here, or I could even using this like onboard LED to display the number of pressing. But for now, I don't need to worry about it. Okay. So now in this case, right? What I need this thing to do is I want to toggle the LED, right? So which LED? The switch 3 LED, right? No, actually the switch 0 LED. So that will be a what? A lat H, right? H1, right? Lat H1, or maybe let's use the first one, H0 equals 0, and then trace H bits dot trace H0 equals 0. Yeah? I mean, anyway, we can also move this thing down to here. Doesn't really matter. Right? Make sense? Okay, so here we toggle the H0. But then what did we say? Every time after we finish the interrupt, we need to manually clear the flag, right? So what's the flag? Not T3, instead it's int0 flag. Yeah? Does this make sense? So let's walk through one more time. We have the header, the 4 different headers, PIC32, cross-C platform, system attribute, and configuration. We have 2 global variables, even though the second variable, flag, we didn't use it anywhere. We have delay function, we didn't use it neither. So the interrupt subservice routine, we have 2 numbers here. The first one is the external vector number. The second one is the system defined priority number. And then the ISR has a distinct name, which is called interrupt0 interrupt. And inside it, we accumulate the number of pressing. And then we toggle the first LED. And basically every time we press it, on, off, right? And then we basically say, okay, at the end of the interrupt, we need to make sure we clear the flag. Otherwise, it's only execute once and then basically says, that bus has already been served. I'm not going to do anything, yeah? So remember, this is important. You have to manually clear the interrupt flag before the interrupt can be taken care of next time when the triggering event happens. So in the main function, set the corresponding ping as the input. Okay, clear the interrupt flag, set a priority level, and enable the interrupt. And then set edge triggered mode, and globally enable the interrupt, and initialize the digital output setting for H0 and give it a low. Does that make sense, everyone? Yes? Now, of course, you say, this wouldn't this mean anything. How about you put a long delay in while 1? Okay, let's put a long delay in while 1. Let's delay a 10 here. So that means actually, it need to delay quite a long time. So we want to add this code in this while one to see actually, even put a delay in the while one. When we press it, this interrupt will happen right away, will respond right away. Yeah? Okay, is this clear, everyone? Okay, any question, comments here? Please follow along, okay? Otherwise, it's going to be harder next time. And like I always like to give you harder problem to solve, right? So make sure you understand the basics thing first. Okay, so let's just build it.
Can you show the wiring one more time?
Show you what?
The wiring.
Show you the wall. It's just a delay 10.
The wiring.
Huh?
The wire.
The wire
The wiring.
connection?
Yeah.
Okay, sure. Let me do it later.
I think I got
Turn
it.
it on.
I didn't turn on. I think I got it right.
Here, right? The wire. This guy goes to pin 1. And this end come to whatever row here. And then one goes to 10, one goes to 11. Okay, that's how you connect it. Right?
There's the voltage supply. These both upgrades from the
Okay, so let's see how this thing executed, right? How this thing behave. So now I press button once, the red LED turned on. I press this button again, it got toggled off. I press it again, but then you see like, how come this one has like twice triggered, right? So you see, and then if I stay here and then go home and come back later, it's supposed to be all off, right? Because it's not toggled. This interrupt event didn't happen. But if I press it again, see that? Toggle off, toggle on, and then toggle off again. You don't need to cross your finger. Trust signs, okay? What? It's not working?
No such file directory. My wiring is so loose.
Does it make sense to you guys? Yeah.
Did my wiring.
Config underscore base.
What's that?
Because we have
First
3
not
wires.
building?
I have 4.
What's up?
You see it? No. What is it? It's trying third.
Yeah, you just assume.
I was under your.
No. Yeah. Third button. Try to see.
Engineers.
Engineers.
You don't have it in your. You put your main in your header file.
Did you delete this? That might do something. No, yeah, that could be. Oh, you didn't even put the delay.
Let H bit.
I was like, this is what worked us.
Let H0. Let H.
It's from the error. I didn't.
So one is a positive, and then 10 and 11.
I don't think so.
Does that make sense? So it's R1.
Just my computer.
R1.
Already?
Yeah, no, mine is.
You just got it. No.
this pin.
Look.
That goes into resistor.
Everybody see that or no? Like when you press the button, you're going to toggle the LED,
That goes into
right?
in pin one.
Yes?
Yes.
These both go
Another success.
Okay, that's good. Yeah.
You don't have
Does this count for the first part?
Yeah, the second week, we blink an LED again.
This is 3.3?
No, but it's actually a very important concept. I mean, you actually could do a lot of useful things based on this concept.
Get that out.
Huh? Yeah. Wouldn't that be important? Certain times, right? You may want to use it.
True.
Yeah.
Scroll up.
Oh.
No.
Was he something? Oh, it got a plug.
When that happens, don't give credit to me. Okay, don't credit to me. Yeah, just say okay, do something.
Why is this red?
Never learn it from me.
No, I changed that one.
Yeah.
I didn't see. Okay, hold on. 1 minute. Yeah.
Yeah.
Oh.
How what?
Oh my god.
Like that's the response for two things. One is like multiple interrupt source, right?
I think that's
When you
just,
enable the multiple
hell?
interrupt source. That's the microprocessor has multiple trigger source.
Alright, guys.
The second thing is to set up the
Is this not working?
edge polarity. So 0 is for rising edge, 1 for fallen edge.
Can you help? I'm very little confused.
Yeah.
So if I need 0 in the example, right? Versus 1.
Yeah.
So if I change it to 0, it should fall.
No.
What do you mean?
The other one, the 1001 will be fallen edge.
Did you get used to work? I'm trying.
No, 1001 will be rising edge. Sorry.
You got C0.
Mine isn't working.
No, when you press it,
That
it's
one
a
should be
fallen
7, but it should have still worked.
because you're pulling up.
H0.
Like this guy, before you press the button, you're sending a high to the input RD0, not a low. You understand? Like you are configured for a fallen edge.
Oh, yeah.
If you want to configure for a rising edge, it will still behave. It's just like the different time you release your finger, that's a rising edge.
Because make
Right?
sure
Or
that you
giving
have the like you have the right.
Yeah.
No, I think
Yeah.
there you go.
Now,
I think
Oh, yours is old?
now when I
That's not gonna matter.
Yeah.
Oh, no, there you
Yeah,
go.
yeah.
No,
The action happened at different times.
in mine
Like one is happening
Yeah, that
at
was-
the moment you
that was
press
my
it, the other
suggestion.
happens
Yeah.
at the
Because mine
moment
is
you
made
release
too.
it.
I had it on A1.
Oh, yeah,
Did you have it devoted?
Say it again?
Can you make it rising and falling like this or no?
Like you mean in this case,
Yeah.
for this guy,
You can't make this rising.
for
and
like for
falling.
one guy, right?
Yeah.
I don't think for one like for one
Because it's either
specific.
rising or falling.
No, for one guy you cannot do
Okay.
it. But then I'm talking about like with the screw, you can some of them
Each of the
rise
pins
and
is
some
connected
of
to
them
the same
fall.
part.
Maybe do I guess display of.
Yeah, it's binary.
Yeah, but like.
wire is
still
still-
uses this one.
It's either binary, it's only based on the income.
Okay, any question here? Everybody got it or no? Yes? Yes? No?
You said this one.
Not specific question, okay, cannot just be, doesn't work. It should be a question.
9 and 12, you can choose which one.
Oh yeah, I got it. Was it wire? Yeah, it was just loose. Yeah, very loose.
Like writing down. If you have like.
No, I'm not getting it.
Yeah, now you need to press the button.
Wait, scroll up. No, the same thing.
Yeah, I'm not.
I don't know what this is used for.
You could.
I guess it's display of multiple times.
Are you sure you didn't make the paper?
I'm trying to. Trust
Why did it have to be recorded like Why did that thing so hard?
Where do you find it?
I have no idea. It's just in my thing. I think it's from the Raspberry Pi.
Oh yeah, that was.
Just like.
Yes, we got it.
Yeah, I think I just put my stuff in. I put my stuff in like
Fix it.
Now I hold here.
I know how to do it. I still remember.
Like.
I actually know.
It gave us a formative on order problems. It gave us a formative.
At least me.
I
I don't think that's the only one.
Wait, no, was that 430?
Like all of this is
Move the X to one side and take
There we go.
Did you guys zero, right? It's zero is a built-in. Everybody's back, right? Except our the only customer who left. So everybody else is here, right? Yeah, customer. That's exactly right. I'm the waiter here. Okay, so let's.
I'll get a steak.
Huh?
I'll get a steak.
It's like you're a fisherman.
Yeah, I'm wearing multi hats. Fisherman, yeah, fisherman. Unfortunately, there's not much fish here in this room.
Yeah, why aren't there any fish? You decorate, why can't you decorate the room?
How much for some crab?
What's that?
You decorate the room and have on.
This is state property. In that case, it's probably like some vandalizing of state property, minimum 6 months, right? I'm not ready for that yet. Yeah. Huh?
You can add one of those to make bats on the wall.
I don't think so. You know, like we're not even supposed to like post a piece of paper, like hang a piece of paper on the door. Yeah, not to mention like put like a bass on the wall.
But it sings. Take it apart, you know? Understand the electronics. It's a lab.
Yeah. Okay. Yeah, you realize like all this lab is named after some kind of song, right? So I recommend like just like Google search those songs. Actually, some of the songs are pretty good. Yeah, like this Leon Knight thing, right? It's pretty good. The country music. Yeah. Even though it has nothing to do with that, right? I mean, it's just like a few LEDs, unfortunately. Yeah. Okay, so the second one. Okay, so let's do a second example here. Folks, let's work on the second example. Let's see, for some reason, right? If we just interrupt 0, RD0, we have to use it for some other thing, right? Let's see, we don't have the luxury of using that as an interrupt, right? Let's further assume that, okay, we have this RPB3, like pin 15 available, right? That's a hypothetical scenario saying, oh, for an application, this guy has been used for some other things, right? But then this guy, RB3, is something available. We want to use that as an interrupt, right? How can we do that? Yeah. Why we pick that one, right? Because the RPB3, it says RPB3, which means it's a remappable pin, right? But of course, you say like, how do you know remappable pin must be able to fulfill that kind of function? I don't know, but there is a data sheet in the, one page in the data sheet tell you, okay, what kind of remappable function, like the input can be remapped to different function, okay? So let's see if we do let's just as a small practice here, let's make it like, okay, interrupt. Where's my PDF file? Here, right? So let's just do like, okay, int 1R. Okay, so RPB3R. What?
Yeah, search on the actual file. Or you
Use the little magnifying glass next to the
Where is that?
zero at. Other one. Up.
Next to the arrows.
And you see 3-2 go right below 3-2 on the top left.
3, 2.
Go down.
Oh, here. Yeah, I'm blind here. So let's see, RPB3R, right? This R setting as the output function, like remappable pin followed by an R is setting something as an output. But is the interrupt an output? No, right? So if you want to set as an interrupt, like int1R, that's the thing, okay? So for example, if I want to set int1r, right? What are the pings available? Those are the pings I can make it map to a interrupt one function. So for example, I mean this page, those 2 pages are pretty important. Like it's a 263 all the way to 264. Those are the input selection ping. Okay, so for example, you either go by the right hand side if you want to like say, okay, only RPB3 are available, right? So I'm going to search RPB3, right? So let's just do another one. Wow, this is endless. Oh yeah, here. See, finally we have RPB3, right? Basically says this remappable ping RPB3 can be mapped to one of those functions. And for now, I didn't tell you what the other functions are, but you know this is interrupt 4. So int 4r is the one I want to set to, okay? So what that means is like if I want to configure the ping RPB3 as an interrupt, the only option I left here is I want to set an int4r equal a binary number 0, 1, 0, 0.
0.
Like a binary 0b, 0b, 1, 0, 0, 0. You say, okay, don't make this like so complex. This is just an 8. Therefore, just give it an 8, right? Binary, not hexadecimal. 0b and 0x means different thing, right? I guess you passed my EOC 265. You understand that? Yes? Yes or no?
Yes.
Okay, so those are the 4 bits. You understand? That doesn't mean this is this. Right? So it's 8, right? So you put int4r equal 8. What does this mean? This basically means you're setting RPB3, that ping, as an interrupt 4 triggering source. Understand? Because like I said, it does not have a fixed, unlike the RD0, it was internally, intrinsically tied to interrupt 0. But now this guy is a remappable ping. You can set it to interrupt 4 by setting interrupt 4r equal 8. Does that make sense? Again, you understand why, right? Because like I said, a lot of times when you design a project, some pings that's the more precious ping. Everybody wants it, right? And then some other function take it. So you say, okay, then now what? Now I still need somebody press a button, do something. But then that RD0 got taken by somebody, which means that you cannot use interrupt 0 anymore. You have to use a different interrupt source. So by looking at this table, you say, oh, if I set interrupt 4r equal RPB3, equal 8, I'm giving this remappable ping RPB3 a interrupt input capture interrupt triggering function. That corresponds to an interrupt 4. Understand? Does that make sense, folks? Mm-hmm. Yes, right? So let's see. If I want you to set, right, RPB15, okay, just look down here, okay, in this, if I want you to set RPB15 to an interrupt 2, what kind of register value you should set? So you want to do an int 2r equal what? 3, right? Again, what does this mean, right? This is like bracket 3 to 0, which means these are the 4-bit register, the 4 rightmost register bit. Understand? Like those are the index. Basically says this is a vector. This is like a 4-bit register. And that 4-bit has to be replaced by the value of 0011. You can either write a 3 or 0b011. In the C compiler, if you directly write a 0011, that's a decimal value. You have to do a 0b or just directly decimal 3. Understand? Yeah?
For the reserved values, is it like don't care? And
What are the reserved value?
like,
Oh, those things are basically, you cannot use them.
okay.
Like those value, like you're not going to save for any. Basically, this means like, okay, you don't have all the 16 possible remappable function. Some of the functions are not assignable, basically. Understand?
Yeah.
Yeah. Okay, very good. So let's just change that one. Your turn. Modify your circuit. Okay, still press the third switch, okay? Press switch 2. Okay, and use this. Okay, press switch 2.
Switch to stack.
Yes, still press switch 2. And use the,
Oh, I think we're pushing switch 3 and 4.
We were pressing 3.
like it says like switch 0, 1, 2, right? The switch 2 is actually anyway it's the bottom switch, the third switch.
Switch 3 then? Switch 3 is. Yeah, it's 1 index, not 0. We were using 3.
Okay, yeah, that's right. So using switch 3, we'll use switch 3, and then connect it to RV3. Okay, configure it to RV3, and then blink the LED 2 in this case. Then LED 2 means the one in the middle. Does that make sense? So you modify your circuit, you modify the code by change 2 lines, and then that's it. And then you make it blink for the second LED. Okay? Do it now, folks. 5 minutes, okay? Yeah. Clyde, this is a digital input. Yes, but I still want you to form a good habit, okay? Understand? Because some of this PIC32 system in the I don't know now, we can experiment by deleting ANSB3, deleting that one, delete trisB3 equal 1, only leave like int 4R equal 8 to see if it's still working. Because previously, this was an issue. Like some of the previous PIC32 I used, you have to add those 2 lines. But later on, I was told actually you can just directly put int 4R equal 8. I'm suspicious, but anyway, we will just let's just do it here.
Yeah, it doesn't work.
Huh?
I comment.
It doesn't work, right?
Yeah, it doesn't work.
Yeah. So anyway, I think I probably got the wrong information from that guy.
What was a different version?
Yeah.
Probably didn't.
So anyway, any other question here? So when you encounter a ping, have both analog and digital function, right? If you want to use it for digital input, you need to disable the analog function. That's probably the third or fourth time I said it already, right? Remember that. That's extremely important. Makes sense, because you say something as an input. How would the processor know you intend to use it as a digital in or analog in? You have to tell it, yeah? Huh? What's that?
It's C, so it doesn't check it.
Mm-hmm. So anyway, so make sure you do all those properly, okay? And typically the way I want to do everything properly by setup a configuration, the interrupt, I do the clear the flag first, and then assign priority then, and after that I will enable the interrupt. Because otherwise, at the beginning, when you properly set the interrupt, right, you enable it first. That's jump out of the order because you didn't even set what priority it has to be, and so on. It will confuse the processor because it's not ready for it. You understand? So flag, clear the flag is the first thing. Set the priority is the second step, and then enable is the last step. Does that make sense, everyone? And next time I'm going to show you multiple interrupts, rather than just a single one. We can have multiple external, we have multiple timer. And I'm not sure if we have enough time. You want to do one more for timer interrupt, or you're okay for the day? If you're okay for the day, then I will do it next time. So next time, let's just do remember bring your box, okay? And we want the piezo buzzer. And last time I will do a simple SpongeBob audio thing. But then your homework is going to be a Super Mario or Tetris. Those things. So I will supply you with a string of this data, or maybe a TXT file, and then you read all this a bit or note number, and then you generate those things to print it out. That would be really nice, right?
Yeah, I didn't get it to work.
What? What's that?
I didn't get it to work.
You didn't get it to work? What's the reason?
I'm looking at.
Didn't get it work. 2 things, right? Did you change the wire connection?
Yeah, put instead of a pin 11,
External
put it in
or
15,
vector,
Yeah.
right?
and then
Lat
that's it.
H bits.
That stayed the
lat
same.
H
That's
one
it. That's everything.
equals
Yeah,
one.
yeah.
That's the only thing I changed.
Toggle equals one.
I looked into
Toggle
it
equals one.
about that.
Where's the cone?
Yeah, I was like, wait a minute, wait.
Toggle equals one. Oh, I can't zoom in.
You said toggle.
Toggle equals one. Cone equals one.
XOR.
Toggle XOR XOR.
But I think it's just doing.
H1 XOR 1. I'm playing, dude. I'm just joking. Right here, dude. Look, right there.
Like 1 year, somebody
Okay.
said final project
No.
was some kind of like a time bomb thing. So he was saying like, you know, like a simulant, right? Like a 2D, like use a word to mix things.
Yes.
Like you kill those like a tube, and then make it like a mix. And then, you know, play
go
this
down.
kind of like scary
Crisp
music.
bits,
It was actually
B3,
pretty
Anso
nice.
B
You
bits,
know?
Anso
Even though we
bits
didn't
equals
see any
0,
explosion, but you know.
Artificial bits, and 4 equals 0, IPC5 equals 7, guitar equals 8, incon
Make it like a
equals 1,
very
0,
bad
ASM
picture.
equals 9, bits equals 1,
But then you
0, try
play
that.
some music, like nothing happened.
You were literally missing that.
What's that?
Is it just one? One thing?
Yeah, we're just lighting
Oh,
up.
it
Well,
doesn't
we're
make-
supposed to light up too, but that's just an easy fix. You have it on H0 pin, but the second light is H1.
The other
So
one.
to change that, all you would do is change all of the H0s to H1.
You're so goated, bless
H0
it.
and then
That never.
H1, H1, and H1.
Alright, you ready to go do this?
Then how's it?
You want to do it in here or?
Zero over there.
Yeah, because we were just.
So by now you guys understand the difference between this one and system programming, right? You know the difference, yeah?
Yeah.
So what's the difference here?
This one has
I
a
didn't
lot
do it.
more-
You have this thing that drives you crazy.
You have to say more about the architecture.
Like you're actually just like write your own driver code, right? Like everything, you
Yeah,
just
still gotta
start from the
freaking
lower
do it.
level
Are you
thing.
doing- are you saying it?
So now you're like, you don't need a while. You do a lot of